The next lecture on Modelica modeling. So today I'm going to give a lecture about Modelica modeling for district cooling and heating systems. So okay, this work actually is largely based on my former PhD student, um, Katie Hinkman's PhD thesis. Um, so it's Modelica modeling for district energy systems. Um, Originally, I planned to have Katie to give this lecture, but unfortunately, there's a conflict with her class schedule. She is currently the assistant professor at University of Vermont. And so this work actually leads to a recent ABIPSA Godf Gottfried Augenberg Award for outstanding PhD thesis. So today's talk is mainly focused on the district heating and cooling, but then another important part of her thesis is biomimicry, which we're not going to discuss today. But if you have interest to learn more, you can find her thesis at our lab website. Also, the related papers are also posted on our website. Okay, so first, why we want to, okay, give me a second. I need to, doing Zoom and the screen is not ideal. I need to okay, that'll be easy. Okay, good. Yeah, so first, why we want to work on district energy systems? Because district system is really important in the US. So we have more than 660 district energy systems currently all in operating. So heating side, they provide heating for more than 5.5 billion square feet of floor space. And on the cooling side, it's about 1.9 billion square feet of floor space. And if you think about the large airport, right? So they all use district heating or district cooling system to support the space conditioning. In terms of energy consumption, most of the district energy system, like district heating, are powered by natural gas in the U.S., as you can see here. So if we want to, reduce the cost or reduce the related carbon emission, we definitely want to improve the efficiency of our district energy systems. If we look at the history of the district energy systems, so it's not new technology. It starts around, 1880s, right? So we have the steam-based heating system, which is still using today. So we supply very high temperature steam to buildings. Then later on, people developed the pressurized hot water for heating and also chilled water for cooling. And then around 1980s, we talk about, reduce the heating temperature to 50 to 60 degree, and then more electrical heating cooling get involved. And currently, there's a lot of topic to talk about combined heating and cooling using we call it ambient temperature loop. So when you have the steam-based heating system, you need to have central plants. Like at our Penn State campus, we have a big boiler plant provide steam. And then when you add the district cooling, so you have chiller plants and also the boiler plants, which are two separate systems. And then when we start to reduce the temperature of those heating medium, then we can start to see system get integrated. And you need more complex sensoring and controls. So today, the new technology we talk about really ambient temperature. That means we'll have single loop. And if if you remember, Dr. Michael Waiter explained the system they are designing in Virginia is trying to maximize efficiency of the entire systems. Now the control has to be tightly integrated. So also they allow the modular expansion, right? So that you can face the entire network, not just develop everything, at once. So over the past 5 years, we have been working with University of Colorado Boulder, UT Austin, and also National Renewable Energy Lab and Lawrence Berkeley National Lab and RPI, and also Amos Technology to develop the software to support the design and operation of we call it grid inductive efficient district energy systems. So as you can see from this schematic, so in this system, we talk about both district heating, district cooling, and also microgrid. So we support renewable energy systems. And in the center, we also have the CHP, which is combined heat and power, so that you can generate heat and also electricity. So this system can be very resilient, right? If you disconnect from the power grid, then you can form your own microgrid to provide a continuous power supply, which is really critical when you talk about resilience. And also by optimizing system design and the operation, you can also significantly improve the efficiency, reduce the cost. And the project is trying to develop a tool so that the industry can use. So the core engine of this tool is Modelica models, and we are releasing those models in the Modelica Buildings Library. For more information, you can find from our project website. So today I'm going to show some of the results from this project. First, let's start with district cooling. Because space cooling is growing faster than any other building end use, and we can see we get more and more hot summers, and the main climate we don't need cooling, but now we start to need cooling. So that just driven the demands of space cooling. So there's a lot of district cooling systems already implemented in US, but there's really no models which can cover the entire district cooling systems. What I mean here is from the plant to the distribution network and to buildings. So in terms of research, it's also very interesting. If you this is the literatures we have found talk about the district heating and cooling. So the red color is district heating and the blue color is district cooling. You can see dominantly most people talking about district heating. So let's opportunity to further study on district cooling side. The objective of this study is trying to demonstrate how Modelica can enable the complete district cooling energy analysis. That means including the plant, the distribution network, and the buildings. And then we can identify the investment-free energy efficiency strategies for a real-world case study. So here we mean that can we optimize the control strategies, right? Then in that case, you only need to change the data points or update your control software instead of spending huge amount of money to do capital investment. And then we can evaluate the potential carbon or operation cost savings due to those energy retrofits. So the case study we did is using a remote campus at University Colorado Boulder. So I was a faculty at CU Boulder before I joined Penn State. That's how we got our project, started the entire research. So this is a small satellite campus for mainly for student housing. So as you can see, they have about 6 buildings here, in total about 90,000 square meters of floor space. So the right figure shows the piping network of the systems. So there's a central plant which provide cooling. And then the 6 buildings are connected using the pipes. So and then the solid line is the chilled water supply pipe, and the dashed line is the chilled water return pipes. And then the cooling demand of different buildings are different, depends on the size and the function. So what we do here, we're trying to understand how the system works. First, the central plant. So here is the system schematics. We talk about of the central plant. As you can see here, we have the center is 2 chillers with a water side economizer. And then for the condenser water side, we have 2 cooling towers, 2 condenser water pumps. And then on the chilled water side, this is a primary only, right? 3 primary pumps for chilled water, then pump the water to the loop. So very typical design. And then you can see the information about the system. So the chiller is about 2,400 kilowatt compressor capacity, then the chilled water pump, condensed water pump, etc. So when you have this information, so we get this information from the facility, and then we also get their design documentations. So by using that, we can develop our Modelica model. So as we learned in this class, so the Modelica model support hierarchy modeling, right? So we're trying to build the model by different layers so that we don't have to expose all the complexity at one layer. And so this is a good example how you can using the hierarchy modeling. So what you see on the right is the top level model, which including the chiller plants, distribution network, and the buildings. And then, of course, we have the weather data. We also describe the ground temperature to study the heat loss through the piping network. And then, if looking at the chilled water plant, okay, the central plants here, right? This is system schematics. But if we do a Modelica model, now we can see we get more details from this is cooling tower with bypass, which is critical for Colorado because in the winter, right, when it's cold or when it's mild season, you don't have the wrong cooling tower. Then you have bypass pumps here. You have the chillers with the water side economizer, condenser water and chilled water pump with bypass valve. So then we also have different control blocks. One way we often do that, we can use a solid line to indicate the physical connection, like the pipes. Then the dashed line can indicate the cycle connection, like the control signals. So that's easy to differentiate which part is control, which part is a physical system. And then if you open this cooling tower with bypass, now you can see the detailed distribution cooling tower model here, bypass valve control here, and then you also have the pipe connections, which you can add the pressure drop to study how much pump power you needed. And then you can also put a temperature sensor to measure the condenser water temperature. If you open this cooling tower model now, we can get a more complex example. You can add an isolation valve that's needed when you do the real cooling tower control. For example, you have 3 cooling towers, right? If you want to repair one, you can just use isolation valve to shut it down so that you can separate that cooling tower from the rest of them. So, but then the control, then we want to control that systems, right? If you want to run a cooling tower, you need to make sure the isolation valve is open. Otherwise, you won't get the water. So Modelica allows you to build a system model as close as possible to the real physical system. And then here is the chillers with parallel water economizer. And then you can see my chillers. This is my water side economizer. If you open this, then you can see more details about the different valves, right? So by controlling the valves, I can determine if I want to enable or disable my water side economizer. Another important part of doing Modelica model is control, right? So you need to have control so that your system can run. That's what also happens in the real world. And yeah, in this project, we did spend a lot of time trying to figure out the control and how to implement them. So basically, we divide them into also different layers. The top layer, layer 1, we call it supervisor control, is to determine which cooling mode my system is to run on. For example, I want to do free cooling or partial mechanical cooling or full mechanical cooling. And then you can move to staging control for chillers, for cooling towers, for pumps, and then to the subsystem control all the way to the local control. So let's just walk through some of them. So first one is cooling mode control. Here we use state graph, the one we really like to use. In the industry, they use sequence, right? English language, but sometimes I found state graph really can help explain the switching of states. So in this case, we trying to really rewrite the sequence in English language to a state graph. So what happens in the real system is that they have off, which the entire system is done, FC is free cooling, MC is mechanical cooling, but they have something called pre-mechanical cooling. So that is, we switch from free cooling. They first go to pre-mechanical cooling. Then wait a little bit to see, do you really want to go to mechanical cooling or you want to go back to free cooling because they don't want to kick on chiller too frequently. So that's something they added. So you will see that sometimes in the real chiller control sequence. And then you can deploy different conditions, right? For example, here we have the 15 minutes waiting time to prevent the short cycling of my equipment. And then this is the implementation in Modelica. We're using the state graph. I think some of you already tried that. So one trick is that you see you can put those signs here so that it's easy to read to understand which states you are representing. So like here we have OFF, FC, so that it can be one-to-one, relationship to the state graph. And then after that, let's move to the staging control. So here I just use a chiller plan as example because we have two chillers here. All right, so the state graph can be 0, 1, 2. The number of chillers are active. Again, so you can define the boundary the conditions to trick this change of stages. Then the law of graph is the implementation of this chiller staging control. And so when you finish that, you can package it as a single icon model here. So then you can put it in the entire system model. Okay, next one, let's go to the distribution network. Here, this is our distribution network model. If you open this one, then you actually see there are connection of two pipe connection. We use lossless pipe here, come to downstream. And then if you open this two pipe connection, now you can see I have supply and return pipes. And then how you can control those valves to regulate the flow demands. And the last one is the building. So here with the ETS is energy transfer station called ETS. So the buildings with ETS, now you can define how much energy, now in this case, chilled water you needed, right? Depends on my building cooling demand. So here we do a PI control here to control the valve, which really determines the amount of chilled water I need. So after we implement all the models, then we need to calibrate our models. In the real world project, so calibration is not easy because number one, we don't necessarily have all the sensors we need. It's super expensive to install a lot of sensors on a real system. Number two, even the sensor readings might not be as accurate as we hope. So therefore, in ASHRAE standard, like ASHRAE guideline 14, they provide what is acceptable when you're trying to calibrate a model in the real world. So the accepted range is actually pretty big. You can see from 0 to 30%. So fortunately, we are able to calibrate our model within the range allowable by ASHRAE. So that means we have some confidence on our model. And then when you have the model, you can start to do the model-based optimization. So the tricky part here is that in a real-world project, you don't want to do experiment on the real system because people will complain if or maybe you will break the systems. But if you have the model, you can do all the tests, and then you can see if those optimal settings would work. And when you have confidence, then you can deploy them. So that's really why we want to use Modelica as a digital twin to do the system operation. So here we tried 3 different approaches. So those, you typically can find from literature or from the industry magazines. People recommend which approach you could use to optimize your system operations. So the 3 approaches we took, one is condensed water supply temperature. Another one is condensed water flow rates, which you can adjust your pump power. And the third one, do we really need a water cycle economizer? So the optimization problem can be defined as trying to minimize my total plant energy. So in this case, it includes my chiller energy, my condensed water pump, chilled water pump, and my cooling tower energy altogether by adjusting those control parameters. So for example, by finding the best condensed water temperature set points. So if you look at condenser water temperature set points, there are different ways to do it in the real world practice. A simplest way is just set them as constant. Okay, so if you look at curve, this is PLR, part load ratio, right? We know it's changing, depends on the demands. And then another one is variable temperature that significantly impacts the performance of my cooling tower. And a lot of times people just set it constant. And then opportunity that, okay, instead of doing the constant, the fixed approach is that why don't I just keep the difference between my condenser water temperature set point and the variable temperature as constant, right? So that I can maximize the potential of outdoor air to cool my condenser water. And then the third approach is more complex. We are trying to adjust this condenser water temperature, the distance, based on the approach, but also on the part load ratio. And so basically, you can write this, into a three formulas. The X is a variable we need to figure out. So which one gives us the best value? Then you can do a simulation. So we run a simulation, and we found that, so the baseline, they actually use a fixed condenser water temperature set point 15.6, right? So now we just trying to find out the better constant set points. Now we find it's about 18.7 for this specific plants. You can get about 2.5% of energy saving. Then if you fix approach temperature to 1.9 degree, you get a 4.4. If you adjust the approach temperature based on two parameters, you get a similar savings. So basically, it means just doing the fixed APP is enough because it's less complex, but get the same amount of savings. And then the Modelica model also allow us to export the energy consumption of different equipment, right? So this figure shows the distribution of the energy consumption, right? As you can see, in the winter, it's largely pump energy because it's cold in Colorado. You really don't need much chiller. You can just run it on the economizer mode. What's like running using the economizer. But in the summer, of course, you need chillers. So now you can see chiller energy dominance. So then we tried a different approaches. For example, let's say get rid of water side economizer. The reason is that to pump the water through the water side economizer, you have pressure drop, right? You need to pump energy. We want to study is that actual pumping energy worth of the efforts, right, compared to savings from chillers. And then we fix the condenser water temperature, we fix the approach temperature, right? Now we also adjust the pump flow rates. So we want to see if we're able to save the pump energy. So the last one is a fixed approach temperature, and instead of running two pumps at a high speed, we run two pumps at a lower speed, 50 each. So you can see this is the last one is what I found is the best one. It can reduce about 15% of energy. In cost is about 8.9 reduction cost. So in our study, the cost including two parts. One is peak power. The second part is the actual energy consumption. So at the end, what do you need to do in this work? Just nothing, no capital investment, just adjust the control. Now you can get about 9% reduction in terms of cost, which is millions of dollars every year. Right? So this kind of approach is really welcomed by industry because they see it's just almost very low hanging fruit.
What does that cost encapsulate? Is that just like energy cost or cost of like the pumps? Like what is like?
Yeah, so this cost is the operational cost.
Okay.
So that we include in the operation cost energy kWh, right? And then also kW, peak power charge.
Okay.
Yeah, so it's based on the utility rates in Colorado. Yeah, so yeah, the industry love to see this kind of control implementation because it's easy to do. Yeah. Any questions about this? Okay, a quick summary of this, right? So the entire work that we developed Modelica model, we release them, and also then we use that model to do the case study. So now all the models has been publicly released in the Modelica business library. And so we showed really nice savings. And the more details you can find from this journal paper. So when we talk about tiller plants with water slide economizer, actually we have more related work. Our previous guest speaker, Dr. Carey Faulkner, actually, in his PhD, he did another work trying to develop near optimal control sequence for the tiller plants with water slide economizer. This is one of our actual projects. Yeah, you can find all the information about the models we developed and also the control sequence we developed. And so Carey also received the ASHRAE Home Adams Award this year, just because of his work contribution to the project. And in January, Carey and I is going to give an ASHRAE seminar talk to report the findings of our project. So that's why I say to Carey, I will see him in Las Vegas. Okay, so let's switch the gear to district heating. So, why we talk about district heat, especially steam systems, it sounds like really old, right? But if you look at what happens in the US, almost more than 90% of our total district heating systems still steam-based. Yes, I agree that trend to convert those systems to hot water or even ambient loop, but it will take billions of dollars for years or even decades time to convert if this condition available. So therefore, the steam-based district heating system still elephant in the room. So if we want to address the energy efficiency problem, we need to work on that. Yeah, it's 97%. So the gaps is that, again, if you look at district heating systems, so we have plant, which can generate steams. We have distribution network. We have the buildings, right? The last one is everything. So they already study, people work on the plant side, even use combined heat and power, CHP. Also, people work on the different software to design the steam piping network, so to make the system more efficient. And also there's some work on the system boundary at the building side. But there is no work which cover the entire system, from the plant to distribution to the buildings. So that's really our goal here, trying to create a complete system modeling framework that we can do the entire optimal system design and operation. To simulate steam-based system is not easy, especially from numerical side, because there's the thermodynamic process is very complex. You have water, you have steam, right? You have phase change process. And so from how this is, people show that numerically is a highly discontinuous function. So simulation is very, very challenging. And in terms of fundamental equations, right? So they have inconsistent equations to describe the thermodynamics. So then it ends up that you can see the chattering phenomena. So the IF97 is a medium model used in the Modelica standard library, which can simulate the phase changing process from water to steam. But if you run this simulation, you can see it's kind of chattering, which means very, very slow. And now if you want to scale it up, right? So to including hundreds of buildings, then the computational cost can be very high. So because you can involve the power closed thermal fluid loops, you can create a coupled system of nonlinear equations, then you're solving, that solution requires iterative nonlinear solvers, which can be very computationally costly. For practice, people want to get a solution in a few minutes, right? They cannot just wait for weeks or months. So that's why we're trying to see if we can develop something that can be used for real world practice. You need a speed, right? You need a good accuracy. They might not need to be perfect, correct, but something reasonable accuracy but a good speed is the goal of this work. Then the idea is that let's look at what's happening in our actual steam systems. So this graph shows that, right, so very simply graph, the boiler. So that's phase changing process, right? That you feed the liquid water into the boiler. Now you get high pressure steams. Then you can use a pressure reducer valve to provide a low pressure steam to the network. And then you have condensation go back, then connect them, feed into systems. So if we are looking for the entire systems, we think about we maybe actually, okay, so a challenge to simulate the system is really at the phase change part, right? When you have liquid to gas, which is very complex numerical process. But if we care, what we care is the entire district network, then we don't need to know the details of phase change inside the boiler, right? That if we don't need to know that detail, then we can treat them separately. Then we can use one medium to study steam, another medium to study the liquid phase, and then use approximation to approximate the phase changing process. So I think that also applies to your work, right? I've told you. So yeah, because phase change is so complex here. And yeah, so that's what happens. The IF97, which is great medium model, it can simulate the subcooled liquid phase, right? The mixture of the wet steam and superheated vapor phase. So this medium model work for the entire spectrum. It's great, but do we need it? Right? So it comes with high computational cost. And then what we propose here is, since we don't really care about the two-phase mixture process inside the boiler, let's just do one medium. So for example, we can use simplified water and with temperature dependent on density model to study the subcooled liquid phase. And then we can use IF97 to study the vapor phase. The second we call the IF97 plus TDD. TDD is temperature dependent density. Or we can make it even simple. Basically, we use, again, the simple water medium model for the water, but then for the subheated vapor phase, we develop a new model, which will be simplified version compared to those IF97. So the entire work start from fundamentals you look at. So basically what we're looking for is that for this boiler, we just make sure, right, so system is equilibrium and then level discharged at the saturation conditions. So, and then we just need to satisfy the mass conservation, internal energy conservation, make sure the mass is balanced, the energy is balanced. So you can treat the entire control volume as a black box, right? Forget the phasing changing process, but make sure the outside looks consistent. And then by doing that, you can package it, you can get our new volume model. So then with this model, then you can add those heat transfer process, for example, to study how much gas you need to burn to provide the amount of heat you inject into this steam. So then you package them, you get a new boiler model. So next, we're trying to evaluate the accuracy and speed of our model. And so here we leverage two open source Modelica libraries. One is the Modelica standard library, and another one is Modelica built library. I think we're using both of them in the class. And then we implement 5 different medium models, as you can see here. So then we compare first the thermodynamic property, make sure it's physically correct. And then we can pack them as control volume. Then we can scale them to district with 10 to 200 buildings. This is meant to evaluate the computational performance. So yeah, the rest I just show the comparison of the 3 representative models I mentioned. So this is implementation I showed. So we have central plant now. So okay, the left one is the system schematics. You can start with the steam boiler plant, distribution network, and then you get heat exchanger, the condensed water trap, right? Then you flow back to the boiler plants. And then you can divide it into plant to distribution network and two buildings, which are very similar to the chilled water plant, district cooling network systems. And then if you open the central plant, you can see the feed water tank, feed water pump, check valve to the boilers, right? Then you have the steam coming out. Then same thing on the building side, you can have the basically we have heat exchanger for volume, then we have the condenser return pumps, then get the heat, steam traps, all these key components. Then when you compare the accuracy, so we found that the simplified model actually gets very good compared to the high fidelity model. So the IF97 we consider is really the reference, right? So the new model works very well. And looking at the error is really less than 0.5%. So which will really meet our goal of accuracy. So the key part here is scalability, right? For industry, no one's going to build district heating system with 1 or 2 buildings. They're looking for 10, 20, like our campus, we have more than 100 buildings connect to our district heating network. So here is trying to really to break the algebraic loop. So what happens that in the Penn library, so when you use IF97 implementation, so the density is a function of pressure and entropy, and the mass is the density, function of density of volume, and the internal energy is function of density, volume, entropy, and pressure. So all things are tightly coupled together. Therefore, to solve this, it becomes super complex. So what we're trying to do is break this connection so that the density is only function of temperature, not pressure anymore. So that decouples the mass and energy balance. And so what it means, this is what happens if you decouple them. So you guys, when you do the Modelica modeling, right, when you translate your Modelica model, you're going to see a message window to tell you the nonlinear systems, if you pay attention on the message window. So here, for example, the MSL design library for this, if one building at 2, 4, that's the number of nonlinear equations. And then if you scale to n, it's n plus 1 to 4. But in the new models, by decoupling them, you can see our number is always 3. So the more the number is higher, then that means your system is more complex, larger, and more difficult to solve. By decoupling them, we are able to just keep my system independent of number of buildings that get involved. Okay, so let's see what happens, if you're able to decouple them, reduce the nonlinear equations. So there's a way to evaluate the computing time. So you can see T CPU is KNP, right? So N is number of buildings I have. And then you can use the log plots, get something like that. So this is what happens. So the X is number of buildings in the log scale. The Y is the computing speed. So you can see using the IF97, so we get a P equal to 3.3, and with the decoupling, we get a P equal to 2.1 or 2.3. Okay, so what it means? What it means that if you want to simulate a large district energy system for annual simulation, for dynamic simulation with Modelica, use IF97, you need about 33 hours, which is, right, from the research point of view, it's okay, but for industry practice, too long. But if you decouple it, you only need 1.1 hour. That's a performance difference. Yeah. So that's what really industry care about. Can you give me the results quick? Because they need to explore so many different options, right? They cannot just waiting for months. Yeah, so also this model has been publicly released in the Modelica Business Library. And so based on Katie's work, my other former PhD, Sarania, further trying to speed up simulation, and she worked on the distribution network. How can we improve the design, the modeling of distribution network? So we tried different approach, like a different lambda model, so that we can keep good accuracy, but significantly speed up simulation so that we can scale it up. And then she used the CO Boulder district energy system as a case study. So this is a very interesting system. They have two plants, two boiler plants at two different locations of the network. One is number one is on the west, another one is the central and on the east. So you can see the system becomes very complex. They have 103 buildings connected. So then we're trying to see how can we speed up the simulation. And so for example, one strategy we found is we can group those buildings so that we can significantly speed up the simulations. And the more details we can find from her paper. And then when you have this digital twin, so right, what is usage of that? Then Saranian did another work trying to see how can I optimize the operation of my boiler plant so that I can deliver all the heating I need, but I can reduce the amount of energy I use and also reduce the runtime of my equipment. So as you can see, he tried different optimization strategies, but it's a very simple, like a practical one that people can implement immediately. And so we found about 12% savings, and then in terms of energy, but also 56% reduction in terms of equipment runtime. So in the real world practice, right, equipment runtime is not a big indicator of the performance, because the less time you run a very expensive equipment, actually you could extend the life and then save millions of dollars. Yeah, so more work you can find also from this paper, at least here. And the main takeaway, so we also developed new fundamental models for district heating systems. So all these models have been publicly released in the buildings library. And so feel free to use them for your work. And then all the papers are mentioned listed here. So next, I want to extend a little bit more about the future opportunities we can work on district energy systems. So the first one is combined heat and power. So as I mentioned, the project we included CHP, right? But I haven't touched CHP in my previous talk. So actually we did work on that. So this work was led by my former postdoctor, Dr. Zhang Wei He. So what we do here is to create a new CHP model which can support the district energy system modeling. So this model including, for the CHP, so we including the top cycling, so really the gas turbine. When you burn the fuel, that you can generate electricity, right? Then the exhaust, so the bottom cycling is you have the exhaust gas that get into a heat recovery steam generator. Then you generate steam, then the steam can push a steam turbine, generate more electricity, and the rest of them you can provide a saturated steam to the campus. So that's a typical structure of a combined heat and power system. And then what he did that he created one set of model which can describe the top cycling, another set of model which can describe the bottom cycling. And then you combine them, you get a CHP. And so here is the results. And so we compared our model with the one, a reference model. You can see we almost match very well. But a big advantage here is, again, computing speed, because so the red line is the speed of our new model, and the dashed line is the existing model in another Modelica library. So we are significantly speed up the entire process. So this work is published in a conference paper last year, and also we are in the process of releasing the model into the Modelica Buildings Library. And so when you talk about CHP, because heat, another thing is electricity, right? So that's where also in the work we talk about microgrid integrated with thermal network. So that's another work led by my current student, Viswanathan Ganesh. So the idea that we want to study the interaction between the thermal fluid system and the electric systems. So imagine if you have a large chiller plants, right? When you're running in the microgrid, when the chiller plants kick on, you're going to see impact of voltage and current to your network. And same thing, if something happened to your microgrid, then it will impact operation of your motor and drive. So that's what we're trying to do, is connect both of them. And that's also enable the built-in-to-grid integration. So this is the model with Viswanathan created. We call it computationally efficient and accurate induction machine. because most of the model in buildings is really induction machine. Then we compare the performance. As you can see, again, it just matches very well with different data. And one thing is quite unique here. So for buildings people, we talk about days, right? Months. So we calibrate our model. If the model matches over a year, we're happy. Look at the time scale here. Can you see that? Maybe too small. What's my units here? Seconds. So you see what we show here from 0 to 0.8 seconds. That's the electrical people talking about, right? Because that's what happens when you kick on equipment. So you can see the oscillation. This is right within point less than 1 second. How many oscillations you have? So this totally different time scale. Right, so you don't want to use this model for annual simulation. That's just too slow. Right? But if you care about the critical operation, then that's something you could use. And yeah, so we also get a journal paper hub with more details, and the model is also going to be publicly released in the Modelica Buildings Library. Yeah, so I talk a lot about steam heating, chilled water, electric system. But in the beginning, I mentioned the currently we talk about fourth, fifth generation system with ambient loop, right? So actually, we also work on that. That's my current PhD student, Julia Ho. I think she's helping many of you. So Julia receives the DOE I Build Fellowship to work, to develop the new energy systems, design tool. Basically, it's based on the fifth generation systems, ambient loop, so that we can support the low cost and reliable energy systems. So yeah, you can find more information from our project website. So one thing we can see that is the system becomes more and more complex, right? So if we only use conventional engineering approach to design system, we're going to see some really challenge. So that's actually Katie's PhD. Is really we're trying to use biomimicry to learn from nature to design our energy systems. So she also received the DOE I Build Fellowship. So she was the first student at CO Boulder to receive I Build Fellowship. And then when I come to Penn State, and Julia was the first to receive I Build at Penn State. So we had two first students. So Katie's work is, so basically we developed, we call it axial-based ecological network analysis for the building and community energy system design. So that's why she was able to receive the outstanding PhD thesis award. So based on this work, we recently received NSF project with Katie and a few other colleagues, trying to learn from the honeybees to design our future energy systems with renewable energy. And here we have also created Modelica models trying to simulate the system behave, so create a virtual test bed, then we can evaluate the new control algorithms based on the honeybee behavior. Yeah, so that's the end of my guest lecture. We are hiring. We have 4 openings. Besides the honeybee, we also have project using Modelica for data center FDD. Then another one is urban scale building energy modeling. If anyone interested in that, so feel free to contact me. And the application deadline is December 15th. Okay, thank you. I'm open to the questions. Do you have any, maybe any question on side? Okay, anyone online? I can.
Yeah, I have 2 questions.
Okay, I can open that.
The first question is for Katie's pipe network, district network, and there's some data input to the buildings. So his question is that, where's the data from?
The data is from the CO Boulder campus. So the project it's so I think that's come here. Yeah, so basically we are able to work with the CO Boulder facility, and they provide us the data, and also we use the information to calibrate our system model.
a question on site.
So,
Yes.
this is just, I guess, a more general question on obtaining the research in the first place. So does the process usually go of you going up to CU Boulder and saying, hey, can I look at your district energy system? Or is it the other way around of CU Boulder is looking for, like, they've noticed flaws in their system and they're looking for someone else to hire them? How does that, like, relationship kind of go? Who asks each other first?
This is very good question. It's really like, do we approach our custom first or our custom come to us first, right? I would say this is both direction. So when I was at the CO Boulder, we're actually looking for opportunity to work with our campus, right, to improve efficiency for campus. I talk to our managers, so then they share their experience. But a lot of times, really, there's not much we can do without resource, right? Resource is always limited for both sides. So, but I see the opportunity, and then by talking to them, I see, yeah, actually, not only CO Boulder, but also other campuses, I know there's needs for this kind of tool. Then we start to develop DOE proposal, and the proposal get awarded. That really enable us to develop those, models, and then we use the campus for our case study. Yeah, we did the same thing for the data center project. It's same thing. We know data center needs a lot of support for tools, and by talking to them, and then we write DOE proposal, and proposal get funded, and then we come to the data center owner, say, let's work together, so we have funding.
Thank you.
Yeah, you guys, if you come to industry, right? So maybe if you have any problems, bring back. Let's work together, write a proposal. Okay, so the question here, let's do it one by one. Is a good rule of thumb of selecting the appropriate energy and mass balance for the thermal fluid component in the Modelica, especially in a model with the fluctuation in temperature and the flow conditions. Free initial, okay. Yeah, I would say I would just start with the fixed initial recommended by LBL. Yeah, so if that does not work, you can try different ones. Yeah, so there's really no better method. I think what the LBL use guy said is good one. Okay, next one, how building load is integrated with the district cooling systems. Is internal load also considered? Okay, so in this case, we do not study the details inside the building, right? So what happens at the facility, the metered, what's happening, the chilled water flow rates and temperature of the chilled water entering and leaving the building. So we just get that information. Basically, it's a lumped load. So then we know how much cooling they needed. So then we add into our model. So we do not simulate individual models. So some approach, like what Julia is doing, that you can create a simplified model to simulate loads, or sometimes you can use Energy Plus to run Energy Plus for annual simulation, then generate those loads, and then save the loads as an input file so that you can integrate to district energy systems. Okay, another comment from, okay, how different the landscape of the DCH is from Sweden to US. The speed change that steam still being used for heat in the US, I guess the amount of heat loss would be quite large compared to the water-based systems. Yeah, yes, I agree. Yeah, I would say the steam-based heating is really legacy systems, right? It's definitely not that efficient compared to the hot water-based or even ambient loop systems. But the challenge is that the infrastructure there, if you want to convert, it costs billions of dollars. That not everyone has the money to do that kind of conversion. So that's why still largely used in the US. Okay. Any other questions from you guys outside? Or anyone from online have more questions? Okay, yes, Ali, yes, great. I'm very happy that example is helpful. You can find the all the details from our papers, which we have listed on our lab website. Yeah, Hongqi just post a link there. Okay, if no more questions, let's end the lecture here. Thank you everyone for attending. We're going to have few more about data center, the net zero energy community, and also smart connect community in the next few weeks.